Chapter 1, The Scale and SLA Challenge. Every single day, more than 3 billion people around the globe unlock their phones and launch Facebook. Within a split second, a personalized feed appears on their screen, populated with photos from close friends, trending videos, group discussions, and targeted announcements. To the average user, this feels like magic. But beneath this clean mobile interface lies one of the most sophisticated and terrifyingly complex distributed systems ever engineered by humankind. Consider the sheer operational scale. At any given moment, there are tens of thousands of candidate posts competing for space on your screen. If Facebook used a naive SQL database query to search through billions of posts across millions of friends, the network would freeze immediately. Yet, the engineering requirement, the strictly enforced service level agreement, mandates that your news feed must render in less than 300 milliseconds with high availability. How do you filter, rank, and assemble a totally unique content stream for billions of concurrent users in the blink of an eye? Chapter 2, Graph Data Modeling with TAO. To understand how Facebook processes connections, we must first look at how data is stored. Traditional relational databases rely on rows, columns, and expensive table join operations. At Facebook scale, joining user tables with post tables across global data centers is an absolute non-starter. Instead, Facebook built TAO, which stands for the Association Object. TAO is a geographically distributed, read-optimized graph database. Rather than thinking in terms of database tables, TAO treats the entire social network as a massive graph made of nodes and edges. Nodes represent concrete entities, such as a user, a photo, a comment, or a page. Edges represent the directed relationships between these entities, such as user A is friends with user B, user A liked photo C, or user B commented on post D. TAO handles trillions of edge queries every day. By storing these relationships directly in memory across massive distributed caching tiers, TAO allows the system to traverse your entire social graph in mere microseconds. Chapter 3, The Fanout Dilemma and Hybrid Architecture. Once you have the social graph, how do you deliver a new post to a user's friends? This brings us to one of the most famous system design trade-offs, fanout on write versus fanout on read. In a fanout on write model, also known as the push model, when you publish a post, the system immediately writes a reference of that post into the inbox memory cache of every single one of your friends. When your friends open the app, reading their feed is blazingly fast because their timeline cache is already pre-assembled. This works brilliantly for regular users who have a few hundred friends. However, this model completely breaks down when applied to high-profile accounts or celebrities. Imagine a global icon with 100 million followers publishing a status update. Under a pure push model, a single button click would force the servers to write 100 million database entries simultaneously. This causes catastrophic write amplification, CPU spikes, and severe network throttling, a scenario known as the thundering herd problem. To solve this, Facebook deployed a hybrid fanout system. For standard users with moderate friend counts, the system uses fanout on write. But for celebrities, public figures, and viral pages, the system switches to fanout on read. Their posts are stored in a dedicated hot cache. Only when you open your app does the backend pull that celebrities post on demand and merge it into your feed seamlessly. Chapter 4, Multi-tier Caching Infrastructure. Latency is the ultimate enemy of user retention. Fetching feed items from persistent storage disks on every scroll is far too slow. To achieve sub-millisecond retrieval speeds, Facebook engineered one of the world's largest distributed RAM caching infrastructures, heavily built around optimized memcached clusters. When you scroll your feed, almost nothing comes directly from a hard drive, your feed is served almost entirely out of RAM. Facebook created Encrouter, an open-source memcached protocol router, to manage traffic across millions of cache nodes globally. To prevent cache stampedes, where thousands of application threads request the exact same missing key simultaneously, the caching layer employs clever primitives like leases. If a key is missing, the cache hands out a lease token to only one worker process to rebuild the data, while telling all other requests to wait or serve stale data gracefully. This architecture guarantees that database layers remain shielded even during massive global viral events. Chapter 5, the 4-stage AI ranking engine. Having a list of candidate posts from your friends and pages is only half the battle. Out of 10,000 potential items, which 20 posts should appear at the top of your feed right now? This is where Facebook's multi-stage AI ranking pipeline takes over. The machine learning pipeline processes content through 4 distinct stages. Stage 1 is candidate generation. The system pulls roughly 10,000 eligible posts from your friends, groups, followed pages, ads engines, and recommended topics. Stage 2 is lightweight scoring. Running complex deep learning models on 10,000 items in real time would crush server compute. So, a lightweight scoring model quickly evaluates basic metadata, filtering out old posts or low relevance content, narrowing the pool down to about 500 high probability candidates. Stage 3 is deep neural network ranking. This is the core machine learning phase. Deep neural networks evaluate thousands of contextual features per post in real time. How often do you interact with this author? Is it a high-definition video or a text update? Are you on Wi-Fi or a weak 4G connection? The AI calculates specific predictive probabilities, the probability you will click, the probability you will leave a comment, the probability you will share, or the probability you will watch the video to completion. These probabilities are combined into a final weighted score. Stage 4 is diversity and policy filtering. Before the top-ranked posts hit your screen, the system enforces business rules. It ensures variety so you don't see 10 posts in a row from the same person, injects sponsored advertisements at fixed intervals, and strips out policy-violating misinformation or clickbait. Chapter 6, Real-Time Event Streaming and Invalidation. A news feed is not a static web page, it is a living, breathing stream. When you like a post or post a comment, that action must instantly influence what you and your friends see next. To handle millions of concurrent user interactions per second, Facebook uses an asynchronous event-driven architecture. Every click, reaction, comment, or scroll event is captured by edge proxies and published into distributed log streams like Apache Kafka or Facebook's internal streaming engines. Stream processing engines consume these events in real time to update feature stores, recalculate user engagement signals, and invalidate stale cache entries. If a post goes viral with thousands of angry reactions, real-time analytics pipelines notify the ranking model to adjust its distribution score dynamically, all without blocking the main user application thread. Chapter 7, Client-Side Optimization and GraphQL. All this back-end power would be useless if the mobile client took seconds to parse and render the response. This is why Facebook pioneered GraphQL. Instead of traditional REST APIs that return fixed, bloated JSON payloads containing unnecessary data fields, GraphQL empowers the mobile app to request exact data fields, no more, no less. On a slow mobile network, the client can ask for just post titles, author avatars, and image URLs, drastically reducing network payload size. Furthermore, the mobile app utilizes prefetching and cursor-based pagination. As you scroll near the bottom of your screen, an intersection observer triggers a subtle background request to prefetch the next batch of 5 posts. By the time your thumb swipes up, the content is already cached locally in device memory, creating the illusion of an infinite, zero-latency scroll. Chapter 8, Conclusion and Key System Design Takeaways. Building a system that serves personalized content to 3 billion people under 300 milliseconds requires mastering system design trade-offs. Let's recap the core engineering principles behind Facebook's news feed. First, leverage specialized databases like TAO to traverse graph relationships in memory. Second, adopt a hybrid fan-out strategy to balance write amplification against read performance. Third, rely on multi-tier in-memory caching with Memcake to keep disk I/O at near zero. Fourth, utilize a multi-stage AI ranking pipeline to narrow down candidates efficiently. And finally, streamline client communication with GraphQL and smart prefetching. That is the hidden engineering marvel powering the world's largest social feed every single second. Thank you for tuning in.